today's seminar. It's a pleasure to have Koji Hashimoto here. We'll be talking about deep learning and holography. And just so you know, this will be recorded. So I hope you're comfortable with that and don't say anything too stupid.
Okay, thank you very much. My name is Koji Hashimoto from Osaka, Japan. I'm happy to visit here. I'd like to thank Mihal for the invitation. The topic here I'm going to present is deep learning and holography. So as you know, deep learning is a new method which is growing quite rapidly these days, and it's a part of machine learning. And also holography is a renowned principle in quantum gravity. And I just wanted to relate these two things to have more fun with quantum gravity. So this work has been done in collaboration with Sugishita-san at Kentucky, Tanaka and Tomiya at the weekend, and we are working together. So I divided my talk into three parts. First, this one is a review of neural networks for those who are not familiar with machine learning, and also how it could be related to gravity. And then in section 2 and 3, I actually tried to connect these two interesting notions. In section 2, I described some principles to relate these two, putting ADS-CFT into the setup of machine learning. It's not just using machine learning for the application of physical programs. Here, I actually want to map all of those quantities in ADS-CFT to a particular neural network in the machine learning. And then I use this mapping for the dictionary to relate these two to apply that to QCD. As you know, in holographic QCD is a renowned gravity description of QCD. But there is a problem here in QCD. So since QCD is not n equal infinity, so this is SU3 QCD, so real QCD. And how can you get corresponding gravity metric from QCD? So QCD, you have the Lagrangian. However, if you really want to solve it, then it's impossible. So you have to resort to some numerical computations of QCD. It's lattice QCD. So we have a lot of lattice QCD data. So the question is how we can actually use those lattice QCD numerical data to produce a dual gravity metric, which is supposed to be equivalent to QCD, and use that emergent metric to compute many other things, observables in QCD. So this third part is a kind of application of the second part. And first, let me start with neural network. So please stop me anytime if you have any questions. So let me go to this section 1. So first, I'd like to remind you of the fact that actually quantum gravity is a network. So this Einstein Institute is a renowned gravitational physics institute. So, I'm very happy to talk about this. So if I look back the history of quantum gravity, then in 1.5 centuries ago, radial calculus was invented, at which the curved space-time is discretized into a collection of many triangles. And this is called radial calculus. And then this kind of technology has been pursued by many people. And for example, causal dynamical triangulation was put on numerical simulations. And then a part of quantum gravity world has been explored. However, this direction, it will continue to matrix models, have not really a strong connection to holography so far. So this is kind of independent quantum gravity research direction. On the other hand, in holography, we have two very nice, intuitively understood picture of discretized space-time. The one is this ADS mirror by Swingle. So you have this spatial direction, and this is emergent ADS radial direction. And you have spin chains here in our space-time. And then it will be discretized into this. So this whole emergent holographic space-time is identified as a tensor network. So this has produced a lot of interesting direction in ADS-CFT, in particular in quantum information. And also one interesting thing is about quantum codes for holography. This is a so-called happy codes. So you have a circular distribution of spins, And then this is a tensor network, and a particularly interesting tensor network is this perfect, using a perfect codes. And here, hyperbolic space has been kind of neatly reproduced by the collection of these tensors. So as you can see from these, to understand, so how we understand quantum gravity is based on its discretization. And there are many ways to discretize the space-time. And this is a dynamical one, this is a fixed space-time. And of course, so machine learning is based on neural networks. And neural networks are kind of networks. So we find here some similarity to machine learning. So I'll make it more precise in the latter part of this section 1. So why machine learning could be useful for quantum gravity? I have 3 reasons for that. The first one is that so far in machine learning community, many neural networks have been proposed for many purposes, and their optimization methods were invented. So it's not just inventing neural networks. So you actually need to find a way to optimize the network bonds so that it can be trained in a proper way. And this is a big subject, and so I'll show you some examples of neural networks later, and there are many of this. And in fact, you see that they actually look like holographic. And I'll make it more precise later. And then the final reason is that these neural networks, they can solve inverse problems. So what are inverse problems? So suppose you consider this kind of physics. B is the input, A is the output, and F is the physical system. So F is something like the equation of motion, or some partition functions or something. So what is a normal problem? So system F is already given, like Hamiltonian is given. Then you need to calculate A for a given B. So B could be some initial condition, and A is the final data, and F is given. So this is a normal problem. And of course, even for QCD, this is a very difficult problem. And more intrinsic and also difficult problem is the inverse problem. So what is the inverse problem? For given many data, the pair of A and B, you need to find F. So this is the inverse problem. And once you can solve inverse problem, then it's a kind of a revolution of physics. So you go upstairs, you find some physical systems, and from that you can deduce many things. So to solve inverse problem is very difficult and important in physics, and machine learning has to do with solving inverse problems. So from now, I will focus on these 3 things. And first, I start with a review of a neural network.
I don't understand the inverse problem. So what do you mean find F? I mean, isn't it just defined by, I mean, what is F? If it's a function, then don't I just think that F is defined by F?
F is defined by what?
A. So once you have A and B, I don't understand what it means to find F.
So this is like an equation of motion, as I said. F is equation of motion. And equation of motion has many coefficients parameters. So it's a differential equation. Mm-hmm. And if, for example, F equals to MA, then F is a function of X, maybe. And F has many coefficients if it is Taylor series expanded. Right? So once you fix the form, yes?
Or do you mean that within a class of some models for F, like just try to find the parameters that describe them?
Yeah.
And then having you can make prediction for other data sets. Right?
Yes, exactly. Yes. Yeah, that's what machine learning is doing. So normally for modeling physical systems, F has a very limited number of parameters, a few of them. But in machine learning, you can make it to thousands of parameters. So that's the benefit of machine learning. Okay, so let me be more concrete. So here is, so if you Google the word network zoom for machine learning, then you can get this picture. So there are many architecture for neural networks. So this is a famous Perceptron model, feed forward, and I'll explain what these circles and lines. And also this is not just that. You have more of them. So each of these have some names for the use or for the purpose of this architecture. So among these, I'll pick up just two of them and explain how it works. So this is the famous Perceptron model, and this is the also famous Boltzmann machine. So I'll explain these two. So what is machine learning in a word? It's a kind of function approximator. So suppose you have an input value and output value. Input value could be a vector. Output value could be a number, or it's a vector. So it's a function of this input vector. So it's f. And these graphs correspond to specification of this function f. A number of parameters are given by a number of these lines. Okay. So this one actually represents a certain class of functions, f, and this one too. So that's how these pictures are understood. And there is a so-called universal approximation theorem, which states that any function can be approximated with more hidden units. Hidden units means these green circles. If you increase the number of these green circles, then this picture gets more complicated. But once you go to a more complicated picture, then this theorem states that this picture can approximate any kind of function. So this is proven. So this is why we use these neural networks. Yes, please.
Very naive. If I understand right, the orange node on the left, that's like the output.
This is output, yeah.
And what would be the equivalent for the Boltzmann?
For Boltzmann machine, the output is actually represented by the whole picture. Yeah. So I'll explain that later. So let me go with the perceptron model first. So what is perceptron model? So this one represents this function. So W is, so here, so let me go by model. So these circles are called unit, and those represent vector components. For example, for this case, these yellow circles are for input units. So it's a two-dimensional vector. So one value for this, one value for this. It's two-dimensional vector. And those lines correspond are called weights. And this is the linear transformation, and the elements of this linear transformation will be optimized by the training. So for example, from this 2 vector to this 2 vector, you multiply 2 by 2 matrix W. And then there is a hidden structure here, which is called activation function. It's hidden line n. Line n is here, here. So this resultant 2 vector, you make a transformation phi, which is defined by this function. So this function is called activation function. This is nonlinear function, and then you get again 2 vector. So these are green circles, and then you multiply this.
Sorry, yes, I mean, the argument of phi is just one number, or is it not a vector?
So this is confusing notation for explicit, but this is a common use in machine learning. So what this means is that for this value you active phi, for this value you active phi independently.
So you apply phi to each component separately.
Yes, exactly. That's the rule. The reason is that this represents a function of neurons. So for example, for this neuron, there is an electric pulse from here and here. And if the sum of these electric pulse goes beyond some threshold value, then this neuron will be activated. So this function phi is this form, and this is called sigmoid function. It's 0 for x negative, but it's positive for x positive. So the threshold is x equal to 0. So in this way, neural network represents a functional form of actual neurons. And finally, you get some numbers here. And this is the output. So how do we train this neural network? Training means you change the elements of these weights, so W1 and W2, so that you train this neural network so that for given input, it gives you a correct answer. So for example, for the case of classifier, if you show a picture of a cat or picture of a dog, depending on that, the resultant this output shows that 0 or 1. If it's 0, it's cat. If it's 1, it's a dog. So in that way, the input picture image can be transformed into 0 or 1. Then you are trained. So how do you train this network? So first you prepare many sets, the pictures and also 0 and 1. So this is the correct set. And you use, so you call this a supervising data. So you use this data and feed them to train the network. So how do you train it? So we adjust W by lowering this so-called loss function E. So E is defined as this. It is the distance between this output value and this functional output. Okay. So if this is if E is 0, then for given all sets of given data, it gives you a correct answer. So this is like our action in physics principle. So you lower the action, then you get the correct minimum of the potential. So this is how it is trained. Now, so let me remind you what this ADS safety corresponds. So this is ADS about gravity. And here you have a boundary of ADS where you have a conformal field theory. On the other hand, in the infrared, there is a black hole horizon. And the correspondence states that, so suppose we have 2-point functions here, is the data. Then if this data is correct, that means that through the GKT-Witten relation, the bulk metric is solved classically with the consistent boundary condition at black hole horizon. So it means that you feed in this data and it propagates in the bulk and it satisfies the correct boundary condition. And this structure looks quite similar to what we have seen, this, right? So you assume that these green circles are bulk, this one is a boundary, and this one is a black hole horizon. So I'll make this correspondence more clear later, like this. And before getting into this correspondence, which I will use for QCD, I'd like to explain the other one, that is this Boltzmann machine. So for Boltzmann machine, again, you have yellow circles and green circles. And yellow circles are called visible units, and green circles are called hidden units. And again, weights are those lines. And with this picture, you compose this energy function. Energy function is given by a bilinear of this unit, visible unit value and hidden unit value h. So this is V and this is h. We have 3-dimensional vector V and 5-dimensional vector h, and W is 3×5 matrix. Okay. So this is bilinear, and you put in the exponent like this, and then you make a summation over only the hidden units here, h. So for this case, I assume that these units take just a 0 or 1 value. Then for that case, this looks like a spin network. And this PVI is actually just so this Boltzmann weight with this h summed over 0, 1. It's a Japanese. It says that I have to talk more clearly. Okay, so what is the training protocol? So I prepare many sets, so the visible unit value and also the physically measured some probability distribution for given VI. So this is like a material. So you have surface atoms, and this is the atoms inside the material, and you cannot observe these spins. You observe just these things. And then you just know what is the probability distribution of these spins in experiments. And you want to train this Boltzmann machine so that it can reproduce those experimental data. So this is the data. So this is supervised training. And the loss function is this. This is a Kalbach-Leibler divergence, it's called. But it's a relative entropy in physical words. So you compare this data probability distribution versus this probability distribution, and you want to make it closer to this one. So this is how loss function is defined, and you make it lower, and then this network is trained. And this Boltzmann machine has been used in many condensed matter systems. I just wanted to explain the details of that, but maybe I don't have time, so I just tell you that. So Boltzmann machine is used nowadays in condensed matter physics. So in condensed matter physics, people use the tensor network states. And these tensor network states, sometimes it works very nicely to produce ground state wave functions. But these days, condensed matter people also use Boltzmann machine states, which is actually a very simple states, if I go back. So for example, this is a Boltzmann machine, and you actually name it to be just a wave function of ground state. And you use this ansatz to minimize the Hamiltonian. Hamiltonian is given by this. The energy, for a given Hamiltonian, the energy is given by this. And assume this as a loss function and make it lower, then you get the ground state wave function. So in this way, condensed matter people uses this Boltzmann machine wave function to find the ground state wave function.
So is it Gaussian or not necessarily?
So you're asking this thing?
Not wave function.
Sorry, what's your question?
So is the probability distribution Gaussian or it's?
It's not Gaussian.
It's not Gaussian.
Right. So that's the point. Here, as you can see, if you don't have this summation of hidden units,
okay.
then it's Gaussian. Yeah.
Excellent.
So this one actually gives you a non-linearity. So it means that if you increase the number of these hidden units, then the reproductive, so the representation power of this neural network is enlarged. So that's why people also wanted to use the many layers of hidden units like this. So it's called deep Boltzmann machines.
What is the computation cost scale like for teaching, supervising these, with the size of the?
Yeah, so there are two ways. So for example, you can increase the number of, you can increase the number of hidden layers, or you can increase the number of hidden units, right? So it's known that increasing the number of hidden layers is more efficient, exponentially efficient compared to the increase of number of hidden units. And also one more thing which I have to point out is that this Boltzmann machine looks very nice, but the training of this costs a lot. So this is like computing a passing a partition function of a classical spin system. Right? So you need to first generate all the spin configurations and then make a summation of all of those. So these two, although they look very interesting, it's very difficult to train. Yeah. So the comment I wanted to make is that there are two theorems. First, Boltzmann machine states are tensor network states. And second, tensor states are deep Boltzmann. So this means that there is an equivalent one-to-one map from tensor network states to neural network states. So now we go back to how they look like CFT correspondence. So this is the picture of a CFT, and this is the renowned GKP within relation. The partition function of CFT for a given source J is equal to the path integration in the bulk of the gravity action. Phi is a gravity field. And the boundary condition at CFT, a boundary here, is such that this bulk field phi is equal to the source function J. So this is the GKP within relation. On the other hand, if you look at the deep Boltzmann machine, then the definition is this. And once you make the dictionary between these things like this, so for example, bulk coordinate Z correspond to these hidden layers. So this is a visible unit, this is a hidden unit. And if you regard this part as a bulk, then the summation over these hidden units H correspond to the path integration of bulk fields phi. So they are corresponding each other. And so these visible units, V, correspond to the source J, which is given at the CFT. So they correspond to each other. And in this way, you can make it more precise. So the natural deep Boltzmann machine with those many hidden units, which was also used for AlphaGo for bit human champion of Go, look really like ADS. So far I've explained, so this is the previous slide. So there are 3 reasons, and they look like program. Yes.
So just to clarify,
Yes.
your point, the main point from the previous slide.
Yes.
For you, the idea would be that like you feed them some configuration of sources, and
yes.
then in the end, this is going to split the value of the bulk field at the horizon, or what? Yeah.
So for this correspondence, this source J is the input value for these visible units, VI. And then HI corresponds to this bulk field phi. So in holography, it's often the case that you solve this bulk path integration classically. Right?
So as he's hinting, like what you want to do is you want to have the partition function as a contraction of the neural network. Yeah.
But as I said, yes, that's true. But as I said, the evaluation of this one is very difficult normally. So this is quantum gravity path integral. So what we usually do is to go to the Largian limit, and then evaluate this classically. So in that classical limit, this one becomes also classical. So you don't need to take. So in the later sections, I just use a classical equation motion in the bulk.
And the input is on a particular time slice of the boundary, or the
yes.
Input is on at all time slices?
So I just use a homogeneous, time homogeneous configuration.
Sorry.
Please.
Maybe it's related. Maybe you just answered it, but this seems like you could do it for any partition function. What's special here with ADS CFT?
You're right.
I mean, like, obviously, it's anything to do with CFT and with ADS or gravity. I mean, why can I not just, at this level, it seems like I could just write that down for any partition function and make this correspondence with any partition function.
Sure, you are right. Yeah. So here I just point out that there is a similarity between the structure of these two things. For example, in ADS CFT, this has to be gravity. And for this, it could be anything. So for example, it looks like space-time, but if you connect this node with that node, then this is very non-local thing, right? So so this neural network could be very arbitrary. It's flexible. So this is a gigantic kind of class of neural networks. And then among those, there are subclass of neural network which can mimic ADS. That's fair to say. So finally, let me go into this solving inverse program issue. So this picture is how we use gravity model to approximate standard model. So this could apply to holographic QC. This could apply to, say, string phenomenology. So what we do is start with the string theory and consider some metric function. This could be usually a solution of Einstein equation. They use this gravity model to compute standard model quantities. So these are predictions. And then these predictions are compared with some experimental data. So this is how it goes. So string model building is this. But unfortunately, you need to be genius to come up with a nice metric which can predict many nice things well compared with experimental data. So the issue is to fix, so how do you find this metric? And this is in fact an inverse program. So suppose you can feed in some experimental data to determine this metric, then that would be a bit nicer, right? They use this metric to compute other observables and then make it a prediction and compare that with other experimental data. So if this could be, if this is possible, then it gives you a better model of string theory.
What about the other supergravity fields?
Really,
you want to do it in string theory, you want to do it in 10 or 11 dimensions.
Right.
You can learn the internal space.
So here, in the demonstration in later sections, I just use a very simple holographic model where I have just a background metric and a dynamical scalar field. So, and also I just use one experimental data. So if this duality is actually true, then all of the correlation functions of CFT, this model should reproduce. Right? But here, I cannot do that. I just chose one experimental data to fix this metric and then compute other things.
Is it unique? If you have other experimental data and I try to do that, will you get the same metric?
No. So generically, no. So for example, for QCD, so I don't believe that there is a gravity dual for QCD since NC is equal to 3. If you take NC to infinity, then there may be some chance. But for this, for my case, I just use real lattice QCD data for this. So yeah, I just didn't explore that direction yet. But I'm sure that if I use other data, then it will give you some other metric. So this is one kind of a direction which I can use for. So anyway, so we need something which can fix gravity metric from experiment. So for my case later, what I use is this lattice QCD data for the chiral condensate versus bulk mass. So in lattice QCD, you can change bulk mass and you can measure chiral condensate. And then these lines are for different temperatures of QCD. So I pick up one data and use this data for experimental data to fix this metric. And then I get some metric, and I use this metric, I can compute other quantity. So in my case, I use Wilson loop. This is another observable which has been calculated in lattice QCD. And what I got is this Q-cuba potential. And then I compare that with lattice QCD data, which looks like this. So this is the whole picture of how we use deep learning to solve inverse programming to fix a metric. All right, so this is the end of section 1. It's getting a little bit hot, this room, but are you fine with this? Do you have any question?
You can turn the AC on.
What's the way there is an AC?
Yeah, just press that button.
Any question? Yeah, please.
So on your previous slide,
This one.
yeah, so you're using this data to train your neural network, right? So if I just use a few less points from this plot, is there some way to kind of show that it's reached convergence or some sort? It's not very sensitive because moving a few plots you get a complete answer.
Yeah, it could be. So what we do is yeah, I'll explain later. But here to fix to find the metric. So you need some regularization. So regularization is a way to get a desired weight distribution for given data. Normally, if you do machine learning, then for a given data, the resultant weight distribution could be kind of different time by time. So I need some regularization. So this regularization is sensitive to how many books you get. Yeah.
So then, what certifies the answer? What gives you any measure of confidence?
So here, of course, I need some physical intuition to constrain what kind of metric it needs to be. For example, if this metric is not smooth, if it's zigzag, then you don't have any physical interpretation, right? So I put some regularization, it's a physical input to fix the model. So it's kind of constraining the parameters of the model. Yeah, that is always necessary for solving inverse problems.
You need some human learning.
Yeah. But you see some amazing points right here, yes. Okay, so in section 2, I'll explain briefly the principle of the dictionary. So this is one-page summary of what is ADSFP. So based on Krebanov and Newton in the late 90s. So I consider classical scalar field theory in d plus 1 dimensional geometry, and it looks like this. So in the case of QCD, this d could be 4. It's 4. And this 5-dimensional scalar field theory living on the curved space-time is with some potential v and its kinetic term. And I chose the metric gauge such that this eta direction has coefficient 1. So this direction is the radius radial direction, and its gauge fixed to be 1. So f and g, these are two unknown functions of the metric. And if you give this, then it gives you a model. So these are unknown functions which will be fixed by machine learning. But there are two constraints. One is ADS boundary, eta is infinite. F and g goes like exponential function with ADS radius L. But I don't know what the number for ADS radius is, but it should be exponential. And also at black hole horizon at eta equals to 0, f goes to 0 like eta squared, and g goes to non-zero positive constant. So these are boundary conditions for this metric, but other than that, these things, these are arbitrary. And how do we get physical data of QCD from this? So we solve the equation of motion, or classical equation of motion of the scalar field phi, and then we get a response function of CFT. So how do we get it? So if I solve equation of motion for phi, then this is a second order differential equation for this eta. So I assume that this phi is homogeneous for these d dimensions. So it's a homogeneous configuration. It's a function of eta. So this is second order differential equation. So if you solve it for a given f and g, then you get two solutions, two independent solutions. So at ADS boundary, since f and g are known, so these give you two independent functions, exponential of something times eta, and this coefficient is a conformal dimension of this operator. And the Krebanov-Witten says that the coefficient of the first non-normalizable component is supposed to be equal to this j, which is the source function in CFT, and the coefficient of the other independent function is the vacuum expectation value of this O, sourced by this j. So, so these coefficients correspond to j and O. At this stage, j and O are independent. However, these are related in the following sense. So this is a second order differential equation, but it should also satisfy this black hole boundary condition. If you assume this black hole boundary condition, then at eta equal to 0, these two modes are related with each other. So this O is given by a function of j. So in this way, this response function, the nonlinear response function for a given source j, what is the vacuum expectation value of O? This nonlinear response function is given by the solution of this system. So this is the summary of Krebanov. So I use this for a neural network. So this is the one-page summary of neural network for the Perceptron. What is this? So you have initial layer, input layer. You have many hidden layers, and then this is the final layer, and this is the output number. So activation function is phi, and W is the weights. So you prepare many sets, X and the final value, and then you make it make the loss function lower to train the system. So this is a neural network. So if you see this Krebanov-Witten and this neural network feed forward, then immediately you see the relation between those two. So this is the second order differential equation for phi in the model. And this equation of motion, of course, depends on the background metric, temporal component and spatial component. And they are combined into this function h. So h is a metric. Metric is hidden here. And this is the bulk equation of motion. And you can make it look really like the previous neural network, this one. So how can I make it? So first, you define pi, which is a derivative of phi. So this is second order differential equation. So to make it first order differential equation, I go to Hamilton equation. So this is the definition for pi. So pi is a derivative of phi. And also this equation is mapped to this equation. And if you look at this equation, then this is an evolution equation of phi and pi to phi and pi. And in fact, this form is a neural network form. So this is a two-dimensional vector. It's multiplied by 2 by 2 matrix. And one matrix element is H, that is the metric. So metric is the weight. And then there is an activation function part here. So this is a combination of linear plus nonlinear. And it gives you the next layer values. So this is the implementation of this bulk equation in motion to neural network. You have two-dimensional vector, mapped, 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 and then go to the end, which is the black hole. And the black hole boundary condition is just pi equal to 0. So this means that once you input the correct relation between pi and pi here, then it propagates, then it should satisfy pi equal to 0. So this is the correct output. So I can use this set, pi and pi equal to 0 at the final layer as a supervising data. And then using that for training, these green lines, those green lines correspond to this H, which is nothing but the metric. So in this way, identifying the neural network as a space-time or the bulk, you can train the network as if it is a space-time metric, and then you get the metric.
Is this evolution canonical evolution? Is it under some canonical transformation?
Yes, so this is the Hamilton equation series. Yeah, so it's a canonical transformation with unknown Hamiltonian. So Hamiltonian has the information of this H and also this potential function. But here it's unknown. So from here, I assume pi4 interaction term, but the coefficient of this pi4 is unknown. So I need to fix it. So finally, this is
Sorry,
yes.
8 of 8 is also unknown.
Right.
It is unknown, right?
8, yeah, this one is also unknown.
Can you explain the incorrect condition pi equals 0?
Why this is it?
Yeah.
So the black hole boundary condition is this. So this is yeah, and this is pi. My definition this is pi. And why this hole is coming from this?
Lorentz?
This is Lorentz. Yeah, Lorentz.
Black hole condition would be ingoing or?
Yeah, it's ingoing. Yeah.
Ingoing.
Yeah, this is so I consider here time invariant homogeneous configuration. So for that case, this ingoing part is eliminated and only this remains. Okay, so this is the dictionary. The emergent space is identified with types of layers. Metric correspond to neural network weights. Nonlinear response correspond to input data. But black hole horizon condition correspond to output data. And the interaction term correspond to unknown activation function. So these weights and activation function, these are unknown, and we fix it.
For integrated, you also impose any constraints on the weight, because H is symmetric. You put some constraints on the weights.
Yeah, exactly. Yes, you're right. So here, normally in the standard neural network, all of these bonds are variables. However, since H appears only here, I just make these green bonds to be variable, and the others are completely fixed. So this sparseness of the neural network is very important for interpreting neural network as a spacetime. So finally, let me go into this QCD experiments. So this is the picture which I showed. So first I pick up one data, and then I fix the metric, then compute Wilson loop to get this and compare that with other lattice QCD data. So there are three parts. So first I use QCD data, then second, let the network run the metric, and then third, I calculate other physical quantities. So what is data? So there are many lattice QCD data, but this one could serve very nice. So I got this data from Unger, who is a specialist in lattice QCD at Bielefeld. And this is the data of bulk mass versus chiral condensate. So chiral condensate is psi by psi operator, and this is the one-point function of chiral. So in our case, this psi by psi is the operator O, and bulk mass is J. So in lattice QCD Lagrangian, bulk mass times psi by psi is the bulk mass term. So this means that psi by psi, the mass operator, whose source is J, that is the bulk mass. So there are many temperature lines, but I chose this black one, 3.33 as a value of beta, because this black one is on top of the critical phase transition temperature. And so this is very interesting. You know that in real QCD, the phase transition from confinement to deconfinement is smooth. There is no first order phase transition. So, but on the other hand, in any holographic QCD model, it's first order because there is a phase transition. So if I choose this temperature, which is on top of critical temperature of QCD, the real QCD, then what happened to the emergent metric? That's a nice, interesting question. So I pick up this. Then I generate positive and negative data. So positive data means that this black line is mapped to this line, and I generate randomly points on this two-dimensional plane. And if this point is closer to this line, then I call it positive data. If it's away enough, then it's called negative data. Positive data correspond to pi equal to 0, the black hole boundary condition, and negative data doesn't correspond to pi equal to 0, so pi non-zero. So in this way, I can prepare positive and negative. And then there are many other papers on holographic QCD, how to map this bulk mass and chiral condensate to the asymptotic value of phi and pi. So this is the non-normalizable part, and this is the normalizable part. Since the conformal dimension of this operator is 3, so there is 3 here, and there is 4 minus 3 equal to 1 here. So these are the modes. And also we have to notice that in holographic QCD with the chiral condensate, we need to add this correction factors. So this is a bit complicated story, but we need this. So anyway, there is a dictionary to map this J and O to the boundary condition of phi and pi. Now, so here is a neural network. So this is the phi input and pi input. And I used the previous Clebank with the decomposition to relate these two vectors to J and O. And then so this is the input function. And the output is pi. And if it is 0, then it's positive data. If it's non-zero, then it's negative data. So QCD lattice data is input here. Then I train these green lines. And this is the movie of how it is trained. So initially, this is a randomly generated metric. So this is H, and this is the number of layers. So this is eta direction, ADS radial direction. So the initial metric is random, so it's zigzag. And if I use this zigzag metric to judge whether the given data is positive or negative, then the result is all positive. So this is wrong. So I want to make this closer to the given lattice QCD line here. So here is the movie. So a certain metric form is here trained so that these green ones can fit nicely the signals. So that's it. So with use of this PC, you can get a very non-trivial metric function, which can nicely fit the given QCD lattice data. And also, the free parameters, for example, the ADS radius, that is L, is trained to be fixed to this value. And somehow this value is found to be very close to QCD scale. I don't know why, but it is trained. And about 5-4 coupling constant, lambda, is found to be this value, which is slightly positive, so it's constant. So this is the emergent metric, and I use this to compute Wilson loop. So how do we do that? So the previous metric is mapped to this f times g to the cubic, or this is the volume form of the metric, and it goes like this. So this is the ADS radial direction, and this is volume form, and it has this very strange shape. So this part is ADS boundary, so it's exponentially growing, so it's natural. And this goes to 0 at black hole horizon, it's natural. However, there is a bump structure here. And we are very much concerned with this bump structure, since I have never seen this bump structure in any solution of Einstein gravity. But here, the neural network is trained and get this metric. So I want to know the physical origin of this bump. If this were ADS Schwarzschild black hole metric, then it starts with exponential and it smoothly goes down to 0. So there should not be such a bump structure. And this bump is actually turned out to be very important. One comment is that if you work with Einstein gravity plus quantum gravity higher curvature correction, then there is a paper which states that there should exist such a bump structure. So this bump structure could be coming from this quantum gravity.
What equations is this metric?
So I didn't solve any.
No, but if you have the metric, what is this metric?
So you're asking this thing?
Yeah.
So this one is, so in type 2A supergravity, there are some known terms for the quantum gravity corrections. And that is R to the 4th. And in some special terms, so those special terms, the coefficients are completely fixed by M theory. So we know some dynamics of that. And if you solve the equation motion for diesel brane singularity, then this bump structure emerges. So that's special case. So it's nothing related to QCD. Yeah, those examples are. However, here, so this bump structure this bump is not a solution of Einstein gravity. So it could be coming from some higher curvature corrections or something. And since we are using lattice QCD data of NC equal to 3, if it has some corresponding gravity metric, then it will be quantum gravity correct.
Can I just ask, this bump looks like an order 1 deformation.
Mm-hmm.
Higher order corrections are suppressed by the flux scale. Why would you expect, if I add R² corrections to Einstein's theory with such a small coefficient, why would you expect them to give a sizable effect?
You mean this? Yeah. Well, that's a good question. I have no answer since I haven't solved any correctly Einstein. This is just an interpretation of the existence. This 1.0 means that the ADS radius size is here. And compared to this length scale, this bump may be interpreted as a slope, but I have to check.
So this asymptotically ADS metric is preferred by deconfining.
This one? No. So for this part, I put the regularization term, which I mentioned. So here and here, these are boundary conditions. So I need to fix it from the first place. Then this part was trained, but these two parts are given. So the question is how you connect this. So anyway, the metric is given, so I can compute the Wilson loop, and the result is this. So this is the interquark distance, and this axis is the potential between two quarks. And then this shows that there is a flat region, there is a linear region, and there is a Coulomb region. And if I compare this with, yes, if I compare this with Lattice QCD, then there are many Wilson loop computations for Lattice QCD. For example, this one, for the temperature, like a critical temperature is this one and that one. So it has a flat part, it has a linear part, and it has a Coulomb part. So these three things are very typical for any QCD, Lattice QCD simulation. And that three phases are clearly seen in this QQ potential. What is surprising here is that if I use Schwarzschild black hole solution, then there is no linear part. So in any reference of holographic QCD at finite temperature, if you compute Wilson loop, then there is a device screening part and then Coulomb part. There is no linear part. The origin of this linear part is actually this bump. So with this bump, the Wilson loop, which is the number-goto string in this metric, can actually feel some infrared wall effect and here, and this produces this. And this is the confining potential.
So what is the boundary in the left? In the right, it's okay. The black hole.
This is the black hole.
But in the left, what's
this part is ADS.
but what's condition in the apple? The boundary.
So neural network is a finite size, so it's around 3 or 4. It goes to explanation. So around here it's pure ADS, and here black hole. The question is what's happening next?
So the black hole is characterized by some mass.
Yes.
And the limit of mass going to 0, what happens to the metric?
So I don't know. Since this is only for a fixed temperature, and temperature fixes the mass of the black hole. So yeah, for your purpose, maybe I have to work with some other lattice.
T going to 0 limit.
Yeah. So if temperature, if I use the lattice QCD data with low temperature, then I can investigate. But I haven't.
So it happens so that the Wilson calculation has this product of F and G.
No. No.
No.
You are right. So for computation Wilson loop, I need these two independent.
But like the machine learning part gives you the product.
Only the product. Yeah. Since this I use only the scalar field equation.
So what do you do?
So for example, I assume the form of G and then get F to compute this thing. And because it could depend on the answers for G, I chose 4 different choice of G and then compute Wilson loop for each choice of G and then get universally. This is the result. So to fix these two independently, then I need more data. Like not just chiral condensate, but some tensor condensation.
So what is the temperature used here?
It's only so it's above. It's on top of critical temperature, so it's like a 200 MeV.
200.
Yeah.
So that is the one which fixes that scale, whatever you were wondering. Right?
Yes. Yes. So in fact, as I said, the trained ADS radius is somewhat very close to the QCD scale. So this is the end of my talk. So I try to emphasize that the gravity is a network, and a special network corresponds to gravity. And the correlation between ADS-CFT and deep neural network, the architecture and also how to implement all of those can be made very similar to each other. And with use of that, I can use Lattice QCD data to fix the gravity metric, and that metric seems to have a very interesting feature, which I have never expected. So the message is this picture, which looked quite naive, but in some cases, it can be used for learning ADS-CFT more for quantum gravity. Okay, thank you very much.
Thanks a lot. There've already been a few questions, but we've got a bit of time if there are any more questions.
Please.
So you showed this training process in a video that has been done on this machine. How long did it take to train the machine?
So it's like just 20 minutes or so.
Mm-hmm.
Yeah. And this is just one cycle. So it took almost like 10,000 epochs, but it can be done just in 20 minutes or so.
Mm-hmm.
And so I did it many times, like 100 times. And then I collected statistical data of this metric, and I found that the deviation is quite small. Yeah, so in total, maybe just 2 days or so with this PC.
Okay.
Since the number of weights which I want to train is just 15 or so, so it's a very small number. It's not really like a real deep learning.
So, but in this graph, there's still a considerable amount of data above the red line.
Oh, here you mean?
Yes.
Yes, exactly. I guess that the reason is that I specified the model to be just 5-4 model. The potential function is completely fixed. So if I allow 5 to the 6th or 8th, then these ones could be better. So it depends on how strict the model is. Yes?
This may be a very broad question. So the picture seems to be that neural networks are a function approximation. So if you're trying to approximate some given function, you can be inspired by what you know of the function. You choose an appropriate network, which is what you've done. So and then you train it on what you know about the function and use it to predict other values.
Yes.
Right?
Yes.
But beyond that, do you make a strong correspondence with this network and actually like geometry and the physical interpretation of this network somehow corresponding to the used geometry?
Yeah. So that's a good question. My first goal was to find automatically, for example, MERA or something. So MERA is a very nice network which should correspond to CFT. So if I start with CFT and consider that's a loose definition of neural network, and if it finds that MERA is the best, then that would be nice. But it turns out that it's not. So the point is that you have to constrain the structure of the neural network to be really carefully, so that it could allow space-time interpretation. Then only in that case it could be interpreted as a space-time. So also for this case, for example, if I remove all the regularization terms, then the resultant trained metric would be kind of zigzag, but it splits very nicely. So there are many other solutions which can fit this data very nicely with zigzag. So on zigzag metric, you don't have any space-time interpretation. So this means that I have to choose a very special regularization term, which looks like Einstein action. So this smooth one. So why it's smooth? Because the difference of the next to each other layer values is small. And that means that you have a kind of differential term for the regularization of the loss function. And so I chose Einstein action, something like that, to regularize this thing. So that's why I got this. So yeah, I need to be very careful in choosing regularization to allow space-time interpretation.
If there are no more questions now, you're around for a few days.
So I'm staying here only for 2. If you have a question today.
Today's a chance.
Yes.
Let's thank Koji again.
Thank you very much.